We demonstrate Kronos, a lightweight framework and system that automatically extracts highly dynamic knowledge for complex event analysis in cyber-physical systems. This research has been done in Washington State and Case Western Reserve universities in partnership with Siemens. Event detection is a critical task for decision-making in cyber-physical systems with various applications in smart grids, cloud services, and sensor networks. We have noticed that these events are jointly characterized by multiple richly attributed signals. They have spatial-temporal correlations with each other, and they may have additional contextual and environmental factors. A missing capability in current data stream processing system is to support automatic extraction, integration, and search for these context-rich events with semantic knowledge from heterogeneous sensor data streams. Such functionality can provide the administrators with actionable knowledge in cyber-physical systems. To this end, we aim to do online event discovery via anomaly detection over these data streams. We then want to find correlationship among these events using some window-based correlation inference, and then we provide the users with analytical event queries to do the search in this rich context. On September 2011, a system disturbance occurred in Arizona, leading to cascading outages that affected 2.7 million people in Arizona and Southern California for around 12 hours. The loss of a single transmission line initiated the event. Here we see a part of US that was affected by the blackout, and we see a fraction of knowledge graph extracted from physical events occurred in this outage. The nodes are events, and the edges are either properties of such events or show the correlationship among various events. Tripping off a 500 kV transmission line at Northgila led to phase difference in Hasayampa that caused two transformer overload at two other locations. Kronos takes as input multiple window-based data streams and provide at any point of the time an attributed knowledge graph with a set of nodes and relationships. There are mainly three types of nodes, including cyber-physical entities such as substations, sensors, softwares, event entities, for example for anomalies, environmental entities such as substation location or temperature. The relationships, however, include network topology among cyber-physical entities, a spatial-temporal correlation that we have found using Kronos among event entities, and environmental relationships, which is between event and cyber-physical or environmental entities. We perform online event detection using an ensemble of base detectors. We use DB-scan, change point detection, and regression to find out any potential anomalies in the signal, and we get users' feedback to improve these base detectors. We also annotate events using some decision trees by incorporating domain-specific rules. At first, we find out events without any label, and then we try to annotate those by saying, for example, this was a tripping off event. We perform online correlation inference to see if two given events are spatio-temporally correlated. We monitor the latest two windows, which are tunable by user. The question is which events were correlated with the newly detected event. We mainly use two algorithms for that: grandeur causality, which is well-established algorithm for causality inference, and graph temporal association rules that we have published in CIKM 2017. We also let users to perform analytical query on this knowledge graph. We consider four types of queries. The first one is a spatio-temporal, when user can ask top K most recent events occurred in specific time and in a specific location. For example, they may say top 10 most recent events occurred between Friday and Sunday in California substation. The user can also perform some facet search or keyword search by asking top K most recent events that contain a keyword from this list of keywords. For example, they can say 100 most recent events that contain phase or overload. This is a type of continuous query that can be executed as the system is running. User can also ask root cause query, top K events causing this event. Then we will return 5 events causing the event phase difference at Hasayampa, for example. Another type of the query that user may ask from this system are top K most similar events to the events with respect to the attributes that that event has. For example, User can ask top 5 most similar events to the event transformer overload at San Diego. This is the architecture of Kronos. It starts by reading data streams and try to find events using detecting anomalies in that signal. It uses an incremental ensemble learning by getting users' feedback to improve the base detectors, and it uses some supervised learning for annotating each event. It then sends the events in a form of a star graph which has one node and a set of neighbors to online correlation detector to find potential relationships between these newly detected events. It uses window-based correlation detector and event synthesizers. We have also this analytical query engine for spatiotemporal, facet search, and query by example to execute on this highly dynamic knowledge graph. Okay, now let's look at the software. Okay, this is Kronos graphical user interface. It has various panels. The first panel is for configuring data sources and window size, another panel for querying and search on the knowledge graph, another panel for showing the knowledge that we have extracted, either as the topology of the networks and the details and the logging information. Okay, let's select the first data source from these data sources that we have here and then run the system. We see this topology of the networks and the way the sensors are connected to each other. By clicking on each sensor, we can see the measured value from that signals. Also, by clicking on event view, we can see as the events are evolving and finding in these systems, and we can see the details of the event if we want. The system is running, and these signals, we can switch between different signals, and at some point of the time, we can see an anomaly occurred and soon propagated to other sensors. Now user can find out the top k events that found by this system as anomalies and the correlationship among them. There are different type of queries that user can issue on this system. Let's select spatiotemporal queries when we say, okay, for example, we want all the events that found on that part of the system. The timestamps of those data stream is based on this. And then we select, for example, Los Angeles and Riverside events in here. By clicking on Analyze, we can see all the events that found within Riverside and Los Angeles and how they are affected each other. For example, here we have overload that might cause power increase, that might cause fault with different values and at different locations. Another exciting thing about Kronos is that you can plug in your own event detection algorithm, your own anomaly detection algorithm, or your own correlation discovery algorithm in here by just implementing or calling from different libraries. As the second scenario, let's look at intrusion detection systems. IDS is a dataset that records daily intrusion activities over a cyber network and includes 7 families of attacks, including brute force, SSH, DDoS. These streams were generated from 41 servers and contain 80 attributes such as duration, number of packets from the network flow. We aggregate the network feature values of 5-minute intervals and extract 80 snapshots. We execute our GTAR algorithm and see Kronos correctly identifies active upload of IRC softwares by attackers that this one led to DDoS attack, taking advantage of IRC botnets in the victim host. If you look at the bottom pictures of this slide, you can see the anomaly part that found by Kronos. Thanks for watching our demonstration, and please contact us for any more information or questions.